Hi everyone, welcome back. We're so happy to have Maria to give us the final lecture on the combinatorial proof of the skewing formula. All right, Maria, go ahead.
Thank you, and thanks everybody for coming to the third lecture. Last time I just wanted to go over the lecture two things from last time to like reorient where we're at. So I gave this combinatorial teaser about things having allowable contents and these words that have allowable content. There was a question about like, are these a certain type of number? And I think Martha was asking, is this like 1, 3, 13 is the start of a certain sequence? Well, a couple people actually suggested that it was the Fubini numbers, and that turns out to be correct. So a couple people at the conference, also even by email after watching the talk online, emailed me and pointed out that there's the Fubini numbers count the number of words with allowable content of a given length, and these are also called like rankings in a competition. For instance, if you have three people and they all compete, and you allow them to have tied places, then you could have two people tied for first, like the second and third person are tied for first, and the first person is then in third place, and that captures this like number of zeros after the a certain number of repetitions. Like if you have two people tied for first place, then you don't have anybody in second place, so you go to the third, and so on. So actually, these are a very well-known sequence called Fubini numbers, and they are counting these like outcomes of competitions allowing ties. And so yeah, so that I didn't even know this connection, but somebody sent me this paper, and it's just fantastic. So yes, Fubini numbers. That's the word that I was missing for these things. They don't have a nice like closed formula. There's it's an OEIS entry you can look up. So anyway, there's this sign reversing evolution we're going to get to. Again, the big overview is that we're over here on the combinatorial proof, and we started it last time, and now I'm going to sort of finish it up, at least finish outlining it. And the key that we boil it down to, we sort of outlined the whole proof last time by defining the delta and rational shuffle combinatorics, and then we talked about a sort of bijective way to get from one object to the other with this bijection f. And this key theorem that we needed to prove that I just sort of skipped and I just stated as a fact and then used it to finish the proof was this inner product of an LLT polynomial with these big letters with the Schur function that we're looking at. We want to show that this inner product is a single power of q or 0. And so this is what I said we'll prove next time. And so I just wanted to reorient and say this is what we're going to be focusing the rest of the proof on. It's surprisingly hard to get a handle on. So now lecture three here. So just recalling the goal of, overarching goal of what we're doing, we are trying to prove this skewing formula in a combinatorial way where the S of a rectangle adjoint operator applied to the rational shuffle formula is the delta formula. The rectangle is, as always, k minus 1 by n minus k, because we're not doing omega in this lecture. So things aren't transposed anymore. We're just k minus 1 by n minus k. And remember, capital K, the capital K that's used in the rational shuffle, is always going to be little k times n minus k plus 1. So this is how you translate between n and capital K using little k. Given that, we know we can restate this formula as S perp applied to EKK of 1, which is the rational shuffle formula, is the delta operator delta prime EK minus 1 applied to EN. And combinatorially, what we were trying to prove is that the S-perf operator applied to the formula for rational shuffle that we went over last time, summing over the word parking functions in a big k by k rectangle, right? This is the ones that are big K by little k, and you have some dict path that goes above them, is equal to, once you perp that, then you get the delta formula, which is these stacked parking functions with area and div. And we did a lot of reductions last time where we understood these stacks and sort of reduced to them from the k by k parking function scenario. And we had our dict paths lying above the stacks, and we kind of got rid of the stacks last time with some of the combinatorics. And so last time we did boil it down to this key theorem about these LLTs, and this is now all working on the rational shuffle side. So we're always in a big K by little k rectangle, and little k divides big K. And we have this LLT that we defined where we have this admissible sequence B, and I'll review this with an example. And we're doing just a Q analog, so just Q to the T div of the big parking function, x to the pi big. And if that is our oh, my notebook fell on the ground. Hang on. Okay, now I have things. So if that's our LLT, then what we're trying to prove is FDB inner product with S of the rectangle is either Q to the CDB, which was some constant we defined last time, if B is admissible, and 0 otherwise. Okay, so let's recall what admissible means. So that means B is a sequence of numbers where they're sort of heights along the dict path, no more than the number of vertical steps in each column. And each BI has to be less than or equal to n minus k, which is the slope minus 1, for it to be admissible. The sum of all the BIs has to be big K minus n. So here's an example where little k is 3 and big K is 9. So I'm going to put 3 and 9. And so n minus k plus 1 is the slope, right? So this is sort of big K over little k. And so that's 3. And then you can solve for n. And so n here is, let's see, 3 minus 1 is n minus k. And so n is 5. Okay. So I'm just going over sort of how to find all these values. And then B can be a lot of different things. B can be something like 211, which is the example we're going to be doing, where we have 2 big letters in the first column and 1 in the second and 1 in the third, where we always push the big letters to the top of each column, right? So you can't have like 3 in the second column. That wouldn't even be possible, let alone admissible, because that would go below the dict path. So B is like dependent on D. D is the dict path. But you could also have like 121 or 202. Those are valid. Those are all admissible B's in this case. Okay, and then for B being 211, so here's an example of one of these pi big parking functions in this formula, right? So here's my pi big can be just this partial parking function where I put numbers that are increasing in the columns, but you can have repeats between the columns like I have here, the 1, 2, and then the 1 and the 1. And because we're going to have to compute t-div on this, which is really annoying when we have this big, sloped, huge diagonal rational parking function thing, we have to look at like slope 3 in this case to compute the inversions. We found it a lot more easy, like streamlined, to shrink the diagram so that the diagonals turn into rows, right? So we want to turn diagonals into rows. And so like this 1, 1, and 1 are all in the same diagonal here, and now they're in the same row. So the shrink map basically takes each successive column of your partial parking function and pushes the ith column down by like I times the slope, so that everything's just lined up, right? And so the 2's are on the second, the 2 is on the second row then. Let me pause and make sure everybody understands what the shrink map is and if there's any questions.
I'm good on the shrink map. Can you remind me? So the B here is just determining like in your parking function, it tells you what the largest entry in each column. Is that
Yeah.
right?
So we're
Okay.
actually just picking a B now and doing a partial parking function. So in the last lecture, I did this reduction where I was like, okay, we're going to consider a standard parking function and take the big letters and the small letters and do this plethystic substitution and separate it all, right? But now we boiled everything. Once we did that, we boiled everything down to this combinatorial thing where we're actually just choosing a B. And this LLT is dependent on both the dict path and the B that you choose. And so it's like choosing a set of positions of where the quote big labels are, looking at just the LLT polynomial that records these, like what's in these big label boxes, and like summing over all of them. So it might actually be more clear if I just continue the example, if that makes sense. Because I am basically, this B being 211 means fix the top 2 boxes in the first column under the dict path, and then the top box in the second one under the dict path, and the top box in the third. So it's 2, 1, and 1. in the 3 columns, and then we fill those with all possible different ways. So pi big is actually just the 1, 2, 1, 1 filling those, right? Like the actual cars. And we're going to compute tdiv of pi big. So again, let me just review what tdiv is now. What tdiv becomes in the rows is an a and b in the same row, which is great. No more diagonals. Or b above a to the left of it in the row above it, where a is less than b. And so in this example, we only have this 2 with this 1 and this 2 with this 1 as the div, because there's no tdiv in the bottom row. So the tdiv up here would be 2 of this pi big. So I do have a lot more examples now. So let's actually compute. This will probably answer Martha's question. If we wanted to compute this FDB for D as above and B being 2, 1, 1, we're going to have the same shrunken diagram that looks like this for all of them. And notice shrunken diagrams could look like, this or something if I wanted, right? I mean, depending, because we're just taking a parking function and shrinking it randomly. So it's a coincidence in this case that it looks like a tableau, but it really doesn't always. But in this case, it does. So this one had tdiv of 2, right? But you can also think, okay, if I'm looking for, say, the monomial symmetric function m31, I also want to know what, like, x1, x2 cubed appears with, because this one would give you an x1 cubed x2, right? And in this case, the tdiv is also 2, because now I have the 1, 2 and the 1, 2 like that, and then no diagonal tdivs, so this also has tdiv 2. And so you have a q squared coefficient on both x1 cubed x2 and x1 x2 cubed, and so you do have a q squared m31 in general, right? And this goes for filling with 2s and 3s or 3s and 4s. If it has that kind of content, you're going to have a q squared. So we have that term coming from, for the M31. Then you can ask, okay, what about like M22? So how many, let me write it over here, how many M22s do we have? Well, there's actually 2 different ways of filling with a content of, 2 1s and 2 2s. And because the first column has to be increasing, right? So you have to have 1, 2 in the first column. And so then you would have like a tdiv here, and this tdiv and this tdiv, so that's 3. So we'd have a q cubed from that term. And from this one and all similar ones, we would have, 1, oh, sorry, I'm on an eraser. 1 between the 1 and the 2 here, and 1 between the 2 and the 1 there. And so you get a q squared. So we have a q cubed plus q squared m22 showing up. Then you can ask, okay, what if we have content 2, 1, 1, right? So I want to know the coefficient of 2, 1, 1. And by symmetry, it suffices to know, so for M211, by symmetry, it suffices to just check all ways of filling it with 2 1s, a 2, and a 3. Because even if you had 1 2 and 2 2s and 1 3 or something like that, it would have to be the same thing. So you look at all ways of filling that, and you just take all the tdivs here, right? So you can try to calculate them. This one just has 2. This one has 2 here. I mean, these are going to all have 2 from the 3, but then, an extra one here and 2 extra ones here. And then I'll just, do them more quickly here to go through. So this one will actually have a coefficient of 2q squared plus 2q cubed plus q to the 4th. And I'm not going to go through all the ways of filling this with 1, 2, 3, and 4 because the only restriction is that the first column is increasing and there's too many possibilities. So I worked out on paper, what are all the possibilities, and it looks like this. So it doesn't really matter. It's some big coefficient for M111, but the point is you add these all together, right? FDB is this symmetric function q squared M31 plus q cubed plus q squared M22 plus, then you add this one, right? Plus dot dot dot. And the disadvantage here is that this is a monomial expansion at its core, right? I mean, this is what the tdiv gives us. We don't have a way of putting it into Schur functions. When we're trying to find an inner product in terms of Schurs, we want to express in terms of Schurs. And Alex has a question. Go ahead. Or maybe it was a...
Is there reversal invariance of that Q polynomial for M111 a coincidence?
I noticed that it's a palindrome, and it's, and all that. And I think, I mean, certainly the answer is it's not always because of things like this coefficient, right? So there's not a general unimodality or palindromicity result. I think there's some kind of there's probably some kind of unimodality going on, and I honestly am just not familiar enough with the research on that to know what's known about it. Also, this is a particularly special LLT polynomial, and I'm not sure what properties it might have. So we haven't really investigated it, but certainly they look symmetric, not symmetric, but they look unimodal. And this one looks symmetric, and I'm not really sure. So that's a really good question.
Okay, thank you.
And I was hoping somebody would ask that because I want people to think about that because I don't know the answer. So that'd be a great thing to investigate. Yeah, so these right, so we're trying to find an inner product with the Schur function, and the problem is we want it expressed in terms of Schurs for that, and we don't have it expressed in terms of Schurs, but that's too hard. So instead of expressing FDB in terms of Schurs, let's expand the S's in the Schur in terms of something that we know how to take an inner product with monomials with, which is the H's, right? So in symmetric function theory, we know that the inner product of H lambda, the homogeneous symmetric function, with M mu is also delta lambda mu. These are dual bases. And so why don't we just write the Schur function in terms of h's and see what happens? That's given by the Jacobi-Trudi formula. So for instance, for S22, just to continue our example, there's a determinant you write down where you take the 2 and the 2 and you make two H2s along the diagonal, and then you increase the H's as you go to the right and decrease them as you go to the left in each row. That's how Jacobi-Trudi looks. And so this would actually be H2 times H2, which is H22, minus H3 times H1, which is H31, right? And so actually, what we're really doing here is taking the inner product of H22 minus H31 with a expansion in terms of monomials that looks like this, and we only have to look at the first two. So actually, we didn't have to do this big computation at all, or even this one. All we needed was the first two, and that's not so bad, right? And so then when we actually compute this inner product, we get the H22 inner product with the M22 gives us a q cubed plus q squared. The cross terms die, and then the H31 with the M31 gives you minus q squared.
Where'd you get the 1, 2, 2, 3?
Sorry, where?
Like on the Schur function determinant.
In this determinant?
Yeah, where'd you get the 1, 2, 2, and 3?
Yeah, so I said it out loud and I didn't really say it. So when you do like S, let me do another example, 2, 2, 1 or something like this. What you do is you take H's along the diagonal that are H2, H2, H1. So these subscripts are the partition, right? And then the H subscripts increase by 1 going right and decrease by 1 going left. So you fill a big matrix of H's and you take, this is how I teach it in a combinatorics class. I say, put the partition on the diagonal and then you increase it going to the right and you decrease it going to the left. And so what I would do is I would fill in, H3. In the first row, I would just go across H2, H3, H4. And then the second row has to also increase by 1 going across as well. So you would put H1. And then this would be H0, H1. And things would just be 0 down here if they were less than 0, right? You would just kind of not have them. And so that's how you do. Oh, sorry, wait, I screwed this up. Oh, they are 0 because I did this wrong. See, okay, this one's H0 because I'm going to the left, and this is 0. There we go. Okay, so that's how Jacobi-Trudi works. Okay, but anyway, so you see that with Jacobi-Trudi, actually it wasn't too bad in this case to be like, oh, we got a single power of q, which is what we want. That's what we're trying to show happens in general. Or it could be 0. It could just be identically 0 if the b is chosen to be bad. So that's what we're going to go through the proof of today. By the way, what is this 3? This 3 should be CDB, which is max t-div of d minus path div of d minus the number of attacking pairs between big and small boxes, where big boxes are the ones that have the letters in them, and the small boxes are just ones that don't have the letters in them, like I'll put X's in the small boxes here. The ones that could have cars but don't. We look for like inversions between those, right? And the big letters. And I just sort of calculated this out for you. We don't need to go into it here, but you can calculate the max total number of TDIMs and the path div and the DSB, and this turns out to be 3 as well. The point is, this exponent is also sort of something we need to show matches some statistics. So that's what we're going to do. We're going to use Jacobi-Trudi. And the only issue with Jacobi-Trudi is it has negative signs, and we want things to cancel and be all like one single coefficient, right? So in general, let me, to answer Alex's question even further, sk minus 1 to the n minus k. So now Alex knows what we put on the diagonal, right? So we have hk minus 1, hk minus 1, n minus k times. So we're going to get a n minus k by n minus k matrix. And then we increase these going to the right, hk plus 1, dot, dot, dot. This one's going to be hk minus 2, and so on. And the nice thing about all the numbers on the diagonal being the same is that it's sort of like everything on every diagonal is the same. So you'll have like a diagonal of all k minus 2's here, right? And the bottom one is going to be let me make sure I'm getting this right. I think 2k minus n, just by, subtracting n minus k the right way. There we go. Okay. So the claim is actually, so we can do a couple of reductions because on the surface, this is going to have a lot of terms. If we take a big determinant and we have pluses and minuses of all these h's, I mean, there's like n minus k factorial permutation matrices that we have to worry about. But actually, it's a lot simpler than that because of things we know about FDB. So I claim that we can take this whole upper triangle after the off diagonal and set it to be 0. So we can set every h with h, k plus 1, k plus 2, and bigger to be 0. And the reason is that when we're looking at FDB, you can't have an m lambda where any lambda I is bigger than k plus 1. So no part of your partition can be bigger than k plus 1. Just by combinatorics, you have k columns. And so you can't have like the number 1 more than k times because you can't have repeats in columns. So that means that we can rewrite this matrix as, you have hk minus 1's on the diagonal, and hk is on the off diagonal, and then zeros everywhere else in this big triangle up here, which I'm not drawing a very good triangle, but yeah. So, and then you do still have the h's down here, and that actually makes the number of possible terms in this computation a lot more tractable. Because now, you have the diagonal term of like the product of all the hk minus 1's, and then you can use some off diagonal terms to like make some interesting permutations, but somehow it's very controlled. Another trick we're going to do is take the complement matrix. So the reason for this will be clear sort of later. It's basically because we want things to eventually only depend on the shape of the path and not sort of, well, I'm not explaining this exactly right. I think you're going to just have to believe me that we want to do this complement operation to turn the combinatorics into something nicer, where we're going to replace each of these subscripts alpha with hk minus alpha. And so what that turns this matrix into is h1's on the diagonal and h0 is on the off diagonal. H0 is just 1 actually, and 0 is in the upper triangle, and then this actually, what makes it nice is this becomes just, sorry, if I take, I'm forgetting how to take k minus 2k minus n. Okay, this is n minus k, that's right, because it's n minus k size. There we go. Okay, so this is actually the matrix that we're going to be dealing with, and how we actually get from the Jacobi-Trudi to this one, I'll explain in a minute. But just to show how we compute with one of these determinants and how nice it is now, especially with this upper triangle being 0, you'll get the allowable contents out that I had in the teaser. So basically, if you have these h1's on the diagonal, your first term is going to be h111 by multiplying h1 times h1 times h1, right? That's from this diagonal. And then you also have, the h0 times h0 times h3 term. So I'm going to actually write this as h300 because I'm going to always list my h's from left to right across the column. So I'm going to think of reading this as h3, h0, h0. Oh, I want to undo it here. h300. And then we have the negative terms coming from the other direction of like h2, h0, h1, right? So you'll have like a minus h201 and also a minus of whatever this is, which is 120. And so we actually have, instead of n minus k factorial terms, we have 2 to the n minus k minus 1 terms, because, you know, the exercise was how many of these, and Jake said at the start, there's basically 2 to the n minus 1 of these, and that's exactly right. So there's only 4 terms now in this example, because it's 2 squared. And the subscripts here, because I listed them from left to right, are exactly the allowable contents, right? The ones where after a 2, there has to be exactly 1 0 before a positive term, and so on. So that's where they're coming from. That's why we ended up with these allowable contents, because of this matrix. So here's the sort of lemma you can turn, and this is now going back to this complementing. What we can say now is that this Schur function of the rectangle by Jacobi-Trudi is the sum over the allowable contents. Well, okay, this Schur function with like with Jacobi-Trudi mod the h k plus 1, etc., are equal to 0, right? I mean, this isn't exactly the Schur function. This is like all we need from the Schur function. This is the restricted Schur function where I set the upper triangle to be 0. But that is the sum over alpha allowable of -1 to the sine of alpha, which is the number of zeros in alpha, of h of alpha tilde. And alpha tilde is what I mean by, go back to the complement again, right? So I'm sort of just making the combinatorics nice, so we have allowable contents, and then just changing back to the complement at the end so we actually have the correct homogeneous symmetric function, and then everything's going to work out. So the corollary now from Jacobi-Trudi is, now that we've expressed this S in terms of H's, we know what this inner product is, because we know what this guy is in terms of monomials. And so what we really have is, it's the sum over alpha allowable over of the sum of all big parking functions, right? This is like big parking functions with content of the complement of alpha, right? The k complement of alpha. And then you have the -1 to the sine of alpha and q to the t div of p. So this is still not like, you know, proving our result, because we want the right-hand side to be a single power of q, or 0, and we have this big alternating sum with signs. So what we need here is a bijective way to cancel the plus and minus terms to get a single power of q, and this is often called a sign reversing involution. So involution is going to be a bijection from the set of parking functions to itself that switches the sign when you apply the bijection. Also, if you apply the bijection twice, it comes back to where you were. So we need to define this sign reversing involution, and this is where the real combinatorics starts. So I'm going to pause here and see if there's any questions. It's a good pause point.
How are you going to get back to from the complement to the original?
We're going to do some complementing on parking functions very soon.
Oh, okay.
Yeah, I'm going to define a complementary parking function. And Jake says, your Jacobi-Trudi formula variance is very interesting. Yeah, well, it helps to set like a whole triangle of numbers equal to 0. It certainly makes it more tractable. And it just happens that we can in this case, right? So yeah, I should have put equals in quotes on this this lemma, but it's really just saying, like, to actually do the inner product, that's all the terms that we need. Yeah. And yeah, it's fun that it turns out to be like the Fubini numbers are showing up, and yeah, it's very fun. So a lot of beautiful combinatorics came up in this. So okay, so the setup is we really need to shrink everything. So if we're going to do a sign reversing involution, here's a much bigger example where little k is 4 and big K is, I didn't even calculate it, it's 5, 4, so it's 20. And so our slope is actually 5, right? And so we have a big diagonal. If we wanted to draw the diagonal, I mean, let's see if it draws it for me. Yeah, so here's our dig path. It's going through like this point and this point and this point. I'm gonna make those points a little bigger. And what we want to do first is shrink this kind of big parking function. So this is an example where, you know, B is 2, 4, 3, 3, which in this case is admissible because the slope is 5. And all the B letters have to be less than 5 for it to be admissible. And what we do here is we write this as, okay, I'm going to imagine like a base. I'm going to take, I have sort of my first column is usual, 1 and 3 is here. And then my next column, I'm going to shift it down 5 places. And if you do that carefully, you'll notice that it lines up this way. And the third column, I shift down 10 places. So, and then the third column, I shift down 15 places. And so I'm imagining sort of empty boxes above a floating baseline here as well, which will be relevant for the end of the talk. But a lot of times I don't draw these empty boxes below. I just have this shrunken diagram because that's all I need for now to compute the t-div, which is the thing we need to preserve with our sign reversing evolution in order for the terms to cancel. So what we do now, Alex asked, how are we going to deal with this complement? And I'm going to deal with this right now. What we're going to do is take the complement of these columns that I just drew in this shrunken diagram. So this shrunken diagram, by the way, I compute t-div the same way as usual. I'm computing like this 1 and 2 as a t-div because they're in the same row and it's increasing. In the same rows, I have this one and this 2 and 3 as well, and this 1 and 3. So I'll have, quite a lot of invs here coming up. So I have 1, 2, 3, 4, 5, 6, 7, 8 coming from horizontals. And then I also have the diagonal ones like this 3 above this 1, or this 3 above this 1, or this 3 above this 2 is 3 more. That's 9, 10, 11. And then I have like this one is 12, I think, right? So I think t-div is 12 if I did that right. I'm actually not sure I did this right. If anybody sees a t-div that I missed or overcounted or undercounted, please let me know. What we're going to do, though, is take the complement in a way that is sort of controlled under the t-div. So the way we complement a column is we take the complementary set from the possible values in our columns, which is 1 through n minus k, and we write it below it, increasing from top to bottom. So I'm going to copy down this diagram from above. So 3, 1, 4, 3, 2, 1, 4, 2, 1, and then 4, 3, 2, and take a different color, say purple, and underneath each of these columns, I'm going to take the complement of the set of from 1, 2, 3, 4, which, by the way, n minus k, this is the slope minus 1, right? So I'm only allowed to go up to the slope minus 1. And out of 1, 2, 3, and 4, here I'm missing 2 and 4 in this column, right? Because I have 1 and 3. And I'm going to write the 2 and the 4 below it, increasing going downwards. So it's sort of reversing and flipping this all upside down. And now the complement of the second row is nothing. I have something empty there. The complement of the third column is just 3 in this box, right? And in the fourth column, I have just a 1 missing. So my purple looks like 2, 3, 4, 1, and I can still calculate div. Oh, sorry, Andon, who is asking the questions. Alex asked something before, and Andon asked something later, and thank you for the clarification in the chat. Yes, both of you are asking good questions. So yes, thank you. Okay, so we still have invs, like 2 and 3 form an inv, and 2 and 1 form an inv. The reading word of the complement partition is actually you read right to left from top to bottom is so 3, 2, 1, 4. We're going to need that for going back to this word trivia that I set up in the beginning. But also, yeah, the complementary inv of P counts the number of inversions in the same way, the number of diagonal inversions, but you're allowed tied inversions. So you're allowed, like, if this if this 2 was a 1, for instance, that still would have been an inversion. So the 1 tied with a 1, that would be the same as if it was a 2. And we also have, complement reading words, and we're going to act on this somehow. Here's the theorem that makes this complementing the right thing to do. This was a little bit tricky to prove, but I'm just going to sort of state it, and we're going to use it as a fact. If you take the inv of P plus the inv of the complement of P, that's constant. It only depends on the shape of D and the B. So basically, it depends on the shape of like the red letters. For instance, up here, you have this shape. If I were to change, say to change this 2 to a 3, that might change the inv upstairs a little bit, but it would also, if I'm taking complements, we would change this 3 down here to a 2, and the total inv and inv hat stays the same. So this is a way that we can complement, and then if we're manipulating inv hat, sorry, I should say inv bar of p bar, right? It's like the other inv that we calculate on the complement. We can actually just do our sign reversing involution on the complement things, which are actually much simpler. And then if we have preserved inv hat, then when we complement again, then we've preserved inv in the original thing. And so this is why we're complementing everything. Complementing just makes everything better. So and it's all consistent. This was, I'm just going to say like one word about the proof. We consider 2 columns at a time. We change one letter in upstairs. We see how the letter downstairs changes. We compare all the invs that could possibly happen. Lots of casework. I believe there's 6 cases in the actual paper. So it's just a big mess, and you just work it out, and you can believe me. So you can definitely read the details in the paper in that theorem. So that means it suffices to find these inv hat preserving sign reversing involution on the complements, and so this changes our combinatorial object once again. And now what's really nice is these complement reading words with the allowable contents, because we've complemented everything and now we have allowable contents. These are exactly the Fubini words. I found what OEIS it is. It's A00670 if anybody wants to look it up. So lots of fun combinatorics on there. And this is due to the IPAC 2025 audience. So thank you for everybody working together, not just the people who commented out loud, but there was also somebody who just emailed me who watched the lecture 2 video and found this one, so it was like everybody working together somehow. I'm not sure exactly who to cite here, but it was definitely the IPAC 2025 audience. So anyway, the Fubini words of length 3, for instance, are these are our possible reading words for a complementary partition. Now, in general, there's going to be some subset of these that we're going to pair up because the actual shape is going to limit it a little bit with the increasing columns. But let's just pretend that we have no restrictions on what the reading word can be. It has allowable contents. Here's how we actually pair it up. I mean, I didn't define it yet, but I'm pairing up like things that have the same inversions. If you'll notice, like 1 and 3 is an inversion and 1 and 2 is an inversion, and also oh, sorry. Because I'm doing the reverse reading word, I'm going to actual like word inversions now. So 3 and 2 is an inversion. That's right. And 2 and 2 is still an inversion because I'm allowing tied inversions. There's so many flips, it's hard to keep track of, but I'm trying my best to communicate it here. And we do it in a way that's sign reversing. So you notice I went from like, this one has content alpha equals 1, 1, 1, and to something that has content alpha is 1, 2, 0. This has 1, 0, and this has no zeros, so the sign flipped. So we're changing the content just by changing one letter in a way that preserves inversions and also changes the sign. There's going to be one fixed point, which is the all-increasing word. So here's how we define this sign reversing involution. You define 2 things, I and M, and you compare them. I is the largest entry such that there's only one I, so it can't be a repeated letter. And if you look at the next largest letter, J, that's smaller than it, then I is to the left of every J. So I have a running example set up here. So say W is the word 37441841. What is I? I is the biggest letter, so there's only one I. Okay, well, there's only one 8, and that's the biggest letter in the whole word. Does that satisfy this condition? Well, 7 is the next biggest entry. Is 8 to the left of every 7? No, it's to the right of every 7, in fact. So I is not 8. So is I equal to 7? Well, 7 is to the left of every 4, right? So I is 7 because it's the biggest number that's to the left of the one that's smaller than it. That's next small. Next biggest. I don't know how to, yeah. Anyway, okay. So I is 7, and then M is just the largest repeated letter. That one's a lot easier to calculate. 4 is the largest repeated letter in this word. 1 is also repeated, but it's not largest. So I is 7 and M is 4, and you compare I to M, and you have 2 cases for your sign reversing involution. So if I is bigger than M, or M doesn't exist, which is this case that we're in, I is bigger than M, we replace I with J, which is the number that's sort of just less than I. In this case, J is also 4, right? So we have the 7. We want to replace this with the number that appears in the word that's one smaller than it. So you would replace the 7 with a 4. So here's what phi would do. And what that does is then, you can see this 7 basically is going to still have its same tide inversions with the 4, because we're allowing tide inversions, the inversions don't change. The other inversions, are unchanged. And because we're moving it just down one step, like the 3 and the 7 or the 7 and the 1 is still an inversion down here or not, as appropriate.
But
So
then
it preserves. Is
that's
there a
why it
question
couldn't
from
be the
Hannah?
8 because that would change. Yeah.
What's that?
That's why it couldn't be the 8 because it would change.
Exactly. If I change the 8 to a 7, then that would actually create a new inversion that's tied, and we didn't want to do that. So we changed that. And then how do we go back and make this involution? Well, if I is less than m in this case, or if I does not exist, then we replace the first m with t minus 1, where t is the smallest letter bigger than m. So now we look at the 4. This is our first largest. M is still 4 in this case now, right? And now I is actually 3. Right? So now I is less than m. Once we've done this phi, we're in case 2 now. And so now to do phi again, we actually apply case 2 and we change the first 4 to 1 less than 8 because that's the next biggest number. And so we changed it back to 7. And so you see that phi is actually an involution, right? It reverses itself. Now, you have to prove all this. You have to prove that once we do one of these steps, then the I becomes less than the M, and then we do it again, and the M becomes less than I again, or maybe
What
they
if
don't
the
exist or whatever.
sorry
And so
to
there's a lot of cases to check.
sorry to interrupt, but what if the 7 was like a 6 at the beginning? Then you'd go 4 and then it would go to 7.
It can't be a 6, right? Because there's 3 4s, and that tells us we skip a 5 and we skip the 6, and then the next number has to be 7. Because that's how the
Oh,
allowable contents work, right? Because, and I should have said this is my allowable content alpha, 2 0 1 3. The 3 has to have 2 zeros following it. So you know the next one has to be 7, and I should write the content here too, and that's, thank you for reminding me to do that. I meant to do that. Oh, sorry. So what we did was we changed this 3 to a 4 in the content, right? Because now we have 4 4s instead of 3 4s. And now we have 3 zeros and a 1. So basically we took this 1 and we added it to that 3, right? In a sort of controlled way in the word. And that makes another allowable content, and then we go back. So the allowable contents is really the also a restriction that we're keeping in mind here. Okay, so, and then you can also see that it changed the sign because this also, goes from, we made 1 1 into a 0 and vice versa in each case. And so we're changing the sign, we're changing the number of zeros. The only case in which this is not possible is if there is no I or M, in which case we do nothing. So actually, technically, there's a third case. But if there's no M, that means no repeated letters. And no I means all the letters are to the right of the letter that's preceding them. So the only example is something like this, right? I mean, you only have you can only have the all increasing word being your only fixed point. And so this is a sign reversing involution with only one fixed point. And so the lemma, I'm going to write out the sort of facts that we know about this. So this is, so phi is a sign reversing involution. It preserves tide inversions. And it has a unique fixed point. 1, 2, 3 up to n minus k, right? So yes, that's, if we found our sign reversing evolution, at least on the level of reading words. And then what's a little bit tricky to show, and you have to sort of fiddle with the parking functions a little bit, but you can also show it, is that phi actually restricts to a sign reversing evolution on the complementary parking functions of a given shape, which then you uncomplement, and that gives you a sign reversing evolution on the db parking functions automatically by taking the complement again. And that has to preserve inversions by that sum of the inversions is constant lemma that we had. And so that gives you, then there's a unique fixed point for any d and b. We're going to call this qdb, as long as b is admissible. So this lemma needs an example. So I'm going to fill in an example here. So going with our running example that I had before, then you have 2, 4, 3, 1 like this. Okay, so there's the complement, right? So our reading word is, we read rows backwards. So 3, 2 across the top first, and then 1, 4. And what we do to that reading word is we apply our phi. And what that does is we say, okay, there's no repeated letters, so we must have an I. What's the largest I that's to the left of all the thing of the next thing smaller than it? That's the 3. So I equals 3 here, and we change the 3 to a 2. And so that, is our involution. And so what that does when we copy it back over to our diagram is we're changing this 3 to a 2. And then we sort of uncomplement, we write the complements above. Now instead of 1, 2, 4 being above, it's 1, 3, 4 above. And that's what we define our sign reversing evolution to do on the red letters, right? That's how we figure out which letter to change. And so that has to preserve the inversions and change the sign. And the only fixed point is the one where we write reading word 1, 2, 3, 4 like that, right? And so this is the fixed point. The complements are going to be 1, 3 again over here, but then we'll have, 1, 2, 3, 4. And above the 1, we'll actually have 2, 3, 4, right? This is looking completely different. Above the 3, we have 1, 2, 4. So same shape, and you complement it, but this is what was so tricky to figure out. We were trying to figure out what's the fixed point, and if we just looked at these red ones and we tried to characterize like when is it a fixed point, it was actually impossible. And when we took the complement, then we were like, hang on, the fixed points are the ones whose reading word is 1, 2, 3, 4, and that's how we actually found the sign reversing evolution. Eventually, was be like, okay, we need to complement to make these things better complement, better, the allowable contents. And then we found this reading word 1, 2, 3, 4 once we, figured out what was the sort of lowest power of Q that we wanted to maintain, that we didn't want to cancel. And that made everything a lot more tractable. Whereas characterizing it above in the red area was actually way too hard. So what this allowed then was this, so we finally have as a corollary of our sign reversing evolution that we have that this inner product is a single power of Q, and that single power is whatever the T-div of this fixed point red thing up here is, right? So we would need like T-div of this red upstairs parking function. The reason it's only that if B is admissible is because B being admissible just means that the columns of the red are no more than height 4 in this case, and that's good because we only have numbers 1, 2, 3, 4, so we wouldn't even be able to fill it. Like it just doesn't make sense. It just, everything is 0 otherwise.
Maria,
Yeah, question.
there's a question from
Oh
Alex.
yes, I didn't see. Go ahead.
In the fixed point, the rows being weakly increasing, is that a coincidence?
Yes, it is a coincidence. I didn't have a bad enough example in this case.
Okay.
Because yes, that was the kind of thing I would ask myself. I'd be like, oh, well, maybe it's the one where the rows are weakly increasing and you have the same number of each letter or whatever. And it was never that. It was only when I took the
Okay.
complement that it was finally clear what was going on.
Okay.
So yeah, things can get really hairy. I mean, I didn't choose a bad enough example is the answer. Yeah.
Sure. Okay. Thank you.
Yeah. Okay, so this is like almost the proof in some sense, or it feels like almost the proof. And so when I finally found the sign reversing evolution, I said to Sean and Eugene, I got it, right? We checked it. They, we all wrote up all the lemmas and everything. And we're like, okay, so now all we have to show is that this last power of Q is equal to CDB, right? This coefficient that we needed, this exponent that we needed. And that took us another several months, it turned out. It was really, really hard to get that this last coefficient was what we wanted. Because what is this CDV? It's this max T-div of D minus path div of D minus DSB. And so we had to somehow relate this path div to this T-div, which, maybe could possibly answer Monica's question that she asked last time about, like, what is this path div? I still don't know what path div is, but at least we can relate it to T-div somehow now. But to do so was actually very tricky. So I only have 9 more minutes. Let me see what I can sort of summarize here. I only plan to summarize this anyway. But let me just do the first simplification. So the one simplification of trying to get this expression equal to this expression is to actually glue this DSB in with the T-div by adding zeros to our parking function. So here's one example. So actually, you know what I want to do? I want to scroll up to the big parking function. Where is it? There it is. And I'm going to put zeros in below the numbers in all the small boxes. So say we put zeros in all the small boxes, then we can still shrink and make some shrunken diagram with those zeros. And what that does is that the zeros are always less than all the other numbers. So this DSB, comparing the big and small boxes, actually compares the zeros and the non-zero entries. And so then, you know, we can just calculate a big TDIV, including the zeros, and don't worry about somehow like just restricting to the big letters. So it just simplifies things a little bit. So what that looks like down here in the shrunken diagram, I can sort of draw it. I filled in 3 zeros below the 3 and 1, and then below the 4, 3, 2, 1, I filled in, sorry, yeah, also 2 zeros. But then I had 4, 3, 2, and because of the way the dict path was, I think I only filled in 2 zeros here, and then the last one also has just 1 zero in the top. And so our shrunken diagram is going to look like something like that. And now the TDIV of this, I'm going to call this Q prime. Yeah, TDIV of Q prime is, oh, well, it says it right here. It's the TDIV among the big letters plus the DSB is the TDIVs among like the 2 and the 0, for instance, form a TDIV, and the 0 and 1, right? So you add all those in as well. And so we have the TDIV of the big plus the DSB. And so that means that I can rewrite this equation where if I want TDIV big of the fixed point to be CDB, then that's the same as, you know, I can put this DSB on the other side and just make that TDIV of Q prime where I add the zeros in. And so now we just have to show that with the zeros added in, TDIV of Q prime minus max TDIV of D plus path div of D is 0. And the other two just depend on the path, and that's good. The Q prime is just like the unique fixed point, which also just depends on the shape. And so now we have something to prove here, which also was really hard to prove. And the proof strategy that we ended up coming up with, which I'm still not entirely happy with it, I'd like a better proof, is that, you know, you can reinterpret the path div on the shrunken diagram. So there's some other way of sort of looking at the path div locally, looking at it more like an inv statistic instead of those things where we put the stars above the path last time. And then the proof strategy is going to be show it holds for the base case, where the base case is the sort of parking function that looks like this. And intuitively on a big diagram, what it looks like is your dict path is hugging the diagonal and keeps coming back to it, and you're filling it with 0, 1, 2, 3, 0, 1, 2, 3, or something like that, right? Just like the sort of most bottommost case. You can just calculate straight out what's the TDIV, what's the path div, what's the max TDIV, and that equation holds, so it's 0. And then we want to reduce to this case by taking an uglier parking function that does go maybe above the diagonal or whatever, and shrink it just like one step at a time, like take the leftmost column and shrink it down by one box, and show that the difference between all these statistics from one case to the next by one little elementary move doesn't change the statistics, the total like sum of the statistics. And so that's what we need to do. And I'm just going to say see paper, because at this point there's nothing I could do better than just like sharing the paper and showing some of the figures we have and showing how ridiculously long this one little this proof was to show this one little exponent. And so I think I'm just gonna share on my computer now, actually. Let me unshare here just to end. So here it is. Hang on, I need to find, there it is. Okay, can everybody see this? Okay, so just to give a sense of how this silly little exponent stumped us for a while. So section 4.4 in our paper, if you're curious to see more of the details of the sign reversing evolution, here's the sign reversing evolution on 4 letters, for instance. And so here's, I'm just going to rewind to Oh, sorry, this is section 4.2 is setting up complements. I don't know where the sections change. Okay, well, anyway, section 4.5 is the final coefficient, where we're trying to show this equation that I just wrote out down. So I was showing how this t div vig of our fixed point plus the dsb can be merged on this side as one simplification. And then here's all the work we had to do to set up these diagrams with the zeros and look at their complements again and calculate the inv and the path inv and the max inv. And we had two moves that we had to do to simplify. So here's one of the moves is if the leftmost column does not contain all of like 1 through 7 here, then you look at the first one that's missing and like you do 1, 2, 3. Okay, 4 is missing. We're going to bump down the 1, 2, 3 and put the 4, and then see how that affects inv in the rest of the picture and see how it affects path inv as well. And it changes everything, and you have to just show that it all cancels. So there's a lot of cases for that. That's one of the reduction steps. Then once you have 1, 2, 3, 4, 5, 6, 7 in the first column, then you shrink it down so that there's not too many zeros. And you basically shrink the left column, and then you shrink the next column, and then you shrink the next column, and so on inductively to reduce it down to that base case. So there's one more example of this. So here's where, say we already shrunk these two columns down to hitting the diagonal. Then we take the next column, and if it's too tall, we move it down one. That actually adds a 0 to our diagram down here because it's changing the size of the dict path now. And that changes the path inv and the max t inv and all these things, and you just show it all balances out. And so I don't, all the details are here if you're curious. So that's how long it actually took. And I do wish there was a more straightforward explanation than that. But the only thing we could figure out was this inductive method where we reduced to that base case. So anyway, that finishes up the proof. So Jake said phew, and I agree. It was a lot of work, and I'm just really happy to be able to give these 3 talks because 3 talks was what it took to even just like give a hint of how involved this proof was and how much fun it was to discover all that. So but we do have a combinatorial proof now in that sense. So there it is. Thank you.
Did you like have a hunch basically that like while you're doing this that everything would all work or?
Oh no. No. In fact, that's a good question. And the way that we ended up getting this sign reversing evolution and all that stuff is we were like, let's just try it for k equals 2. If we could just get k equals 2, like that would still be cool. And then if we could just get k equals n minus 1, and then we kept doing it. And the thing is, like, after we would do a case like k equals 2, then I would be like, wait a minute, but this, like, I should be able to generalize this. And Sean would be like, I really think this is not just for k equals n minus 1. I think we can do it in general. And then Eugene would be like, if we did this other simplification with the LLTs, I mean, it was very much a team effort. I mean, there was so much like one person would get one more little lemma, and then the next person would be like, I really think we could generalize this to the big case. And it just kept happening until we got the whole thing. And so, yeah, it was a lot of work.
Okay.
That's awesome. Thanks, Maria.
Thank you.
Any questions for Maria?
Is what Sean's gonna talk about next time is it related to this or?
Yes, it's all the geometry stuff. So let me just go back and reshare one more time. Just back to my notes. So going back to the big map of where we're at. So we have finished the going through the algebraic proof and the combinatorial proof. And now we'll do the geometric proof and the geometric connections. So maybe I shouldn't call it a geometric proof of the skewing formula. It's more like now that we have the skewing formula, we can understand geometric interpretation of some of these formulas that we didn't have before. And yeah, we generalized work of Hikita on affine Springer fibers to what we call affine delta Springer fibers. And this was also motivated from this one variable case that we were doing Springer fibers in, but we have to affinize everything because now we have two variables. And so yeah, Sean's going to be talking about that for at least 3 lectures. And I'm still grateful, Anna, that you gave us an extra day just in case, because I'm sure Sean would appreciate it, because you know, all aspects of what we did were somehow very involved. So there's a lot of details in the geometry side as well. There's a lot of perverse sheaves and line bundles and you know, Borjo McPherson work and all kinds of very fascinating things going on. So I'm looking forward to seeing Sean's talks because he's going to be fantastic. So please come.
Thank you so much. Thanks, Maria, again.
Thank you for having me. This was so much fun.
All right, so we'll see everybody on Thursday, and then stay tuned for the geometric series. Bye, everybody.
Bye, Anna.
Bye.